Dear students, let's talk about nuclear force. And the very first question arises is that what keeps together the nucleons of a nucleus? And obviously, the force uh, that must be responsible uh, for a composed nucleus uh, is 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 nuclear force. And let us have some. Let us start with the very fundamental question, and try to move on from here to understand this nuclear force. And if we start with the concept that we have nucleons, and among nucleons we have protons and we have neutrons, and neutrons do not have any charge, and protons have positive charge. And if we think of electrostatic force between protons in a nucleus, let us assume that we have the two particles, and assuming them to be two nucleons, uh, the Coulomb electrostatic force as well as the gravitational force cannot keep these nucleons bound inside the nucleus. And and the size that we have here of the order of 10 to the power of minus 15 meters. Now, to account this kind of unevenness that could be understood, that it wouldn't be possible for nucleus to be nucleus, because if we assume that it has only protons, they have the electrostatic force, and that electrostatic force is repulsive in nature. And uh, and then we have neutrons. If we think in terms of the gravitational force, uh, again we have a problem. That's the weakest. That's manifold weaker than that of electrostatic force. So here we have we want another force that could account for nucleus to exist. And the point is that nucleus exists in nature. And then in order to account for the stability of the nucleus, we had the concept of the new force, and this force is called as nuclear force. And this was basically this name, nuclear force, was given by a Japanese physicist. His name was Yukawa. And this nuclear force that I'm talking about, it was assumed to be strong, attractive force of magnitude, of whose magnitude is greater than that of Coulomb repulsive force. And what Yukawa predicted is that the nuclear force, it arises due to the exchange of particles. So we have nucleons, and between these nucleons there is exchange of particles. There is exchange of particles, and these particles are called as pi mesons. Okay. And uh, and these pi mesons keep on, they keep on exchanging between the two nucleons, and this leads to the attractive force. And since these forces are highly complex, they are strongly complex in nature, and certainly there is no simple way to demonstrate how the exchange of mesons take place between the nucleons that lead to the attractive force between these nucleons. So the process can be understood if we want to have some way to understand it with the help of a simple example. Imagining that, if we imagine that we have two dogs, say this is dog one, and then we have dog two, and there's a bone. Okay, the food for the dogs. Now, 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 now these two dogs and a meson particle between them in the form of a bone. Okay, so this is a meson particle. It's a bone, and we have two dogs, and each dog is carrying a name, a nucleon. It's a nucleon, either neutrons or protons. Uh, the point here is that each of the two dogs, now both of the dogs have caught up the bone, and each of the two dogs are trying to snatch the piece of the bone from each other, and the bone is rapidly being exchanged uh, between the two dogs, as neither of the dogs, I mean as neither of the nucleons uh, uh, them can part it with. Thus, the rapidly exchange of this bone keeps the two dogs together, and the two dogs find themselves to be bound, and similarly, the same way there is exchange of pi mesons that keeps the two nucleons bound to each other. Now, let us talk about some important properties of this nuclear force, and some of the properties that we would like to talk about here. Properties of nuclear force. So what we understand is that uh, we have a nuclear force. This is strong, and it's stronger than that of electrostatic repulsive force between the nucleons. And what we understand is that there is a new kind of force known as nuclear force, and this nuclear force comes in action because of exchange of particles known as pi mesons, and this exchange of particles leads to the attractive force between the two nucleons. Now, the very first important point is that this nuclear force is strong fundamental force in nature. So, so to say that the magnitude of this nuclear force is, if I have to have an F nuclear, its magnitude is nearly 100 times. It is 100 times greater than that of electrostatic repulsive force, F electrostatic, and this electrostatic is a repulsive force. It will not allow the nucleus to remain stable, but we can see that this nuclear force is 100 times stronger than that of this force. And and what is more important here is that this nuclear force, being most strong than the Coulomb's repulsive force, uh, uh, is able to bind the two nucleons inside the nucleus. The next important thing is that this nuclear force is mainly an attractive force. So this is the force that's only attractive in nature. And if we go with the variation of potential energy with distance, if we have some distance uh, where we have to demonstrate it, this is potential energy axis, and this is R0. So this is R0, the reference radius of the nucleus, and this is this will be 100. Now, what am I trying to say here is that the variation of potential energy that we have that we have between the nucleons can be seen here. That how does it behave? So under this curve, the force is attractive, okay? But when it comes out of this negative side, the force is repulsive. So we can see that nuclear force is an attractive force up to R0, and then its magnitude goes on decreasing, and finally, if you bring that, if they are more closer than this, then we have we have the repulsive force in action. Now, what does this thing reveal basically here is that the potential energy is least at R0, which is nearly zero point 0.8 Fermi. Okay, so when the distance between the two nucleons is greater than R0, the nuclear force is attractive. Okay, it is attractive, that I'm trying to express here. Now, as this distance between them decreases and becomes less than this R0, this force becomes repulsive in nature. And that should be the case when we'll bring the two nucleons close together, then there has to have a limit where this attractive force will bounce back in terms of the repulsive force. Now, this nuclear force is charge independent, so it does not depend on the charge of the nucleon. Sorry. So. So to say, the interaction between the two nucleons is dependent of whether it doesn't depend. It's basically independent of whether the nucleon has a charge or not. The force between neutron and proton, proton and neutron, proton and proton, neutron and neutron. This is one and the same thing. They have the same magnitude of force. That's why what we say is that nuclear force is charge independent, and this force is short range force. This is the important point to be taken into account. It's a short range force. What does that mean? That means the nuclear force between the two nucleons exists only when the distance of the nucleons is comparable to the size of the nucleus. If this is the size of the nucleus, then there will be nuclear force, and that will be attractive force. And the order of that size is nearly 10 to the power of minus 15 meters, what we call as 1 Fermi. Now, these forces cease to act as the distance between the two nucleons exceeds this limit. So once this limit is gone, you will have no nuclear force at all. And in addition to this, a nucleon can interact with only its neighboring nucleon. So the nucleon that's here, maybe you have a nucleon here and here, it will prefer to interact with the nucleon that's closer to him. It can be as a replica of an atom in a solid, forming bonds where an atom interacts with the atoms that are surrounding this atom. So same is the case with this with the nucleons. So thus these forces are short range, because these forces cease after the average size of this nucleus. And next important point is these nuclear forces, it's a saturated force. It's a saturated force. And what happens is, once it crosses the limit, the force between the two nucleons ceases to zero. I mean, this force goes down to zero when the distance between the two nucleons is just about a Fermi. There's a nucleon can attract only the nearest neighbors, and it has no influence on other nucleons. And the next important point is that it's an exchange force. Nuclear force is an exchange force, and exchange I talked about in terms of mesons. So what we have here is that nuclear forces are due to the exchange of the particles known as pi mesons between the nucleons. So that's why they are called as we call them these forces as exchange forces. And this what we have, gravitational force, is a central force. It always acts along the line joining the centers of two bodies. Electrostatic force is central force, but nuclear force it's not a central force. So I should say the opposite of gravitational force. So we can say that the force between the two nucleons does not act along the line joining their centers. So that's not the case here, uh, and is therefore called non-central force. So nuclear force is non-central force. And finally, this nuclear force is dependent on spin. It is dependent on the spin of the nucleons. So this has been observed, that the nuclear force between nucleons, having parallel spins, to be very precise here, is greater than that of the force between the nucleons having anti-spins. Thus, what we say is that these nuclear forces are spin-dependent forces.